Hello, everyone. So, first of all, unlike my other streams, this stream will be in English. And then um, let me check if everything's okay with the live stream. So, let me check if everything's okay with the live stream. So, yeah, everything seems fine. And we can continue. So, in this stream, we're going to talk about parameter efficient fine tuning methods. I have a couple of papers in mind that I want to look at. And rather than this being an explanatory and introductory stream, I will be looking at the details and actually how the papers were written and presented more than uh, introducing a lot of topics. But these papers, most of them are quite simple, so I don't think it will be a problem to understand it if you're a beginner. But yeah, then let me set everything up and then we can start, I guess. Uh, so, just a second. Rather than starting with the default low-rank adaptation paper, I will be looking at other papers addressing its deficiencies, uh, etc. So, and from the last stream, I had started reading a blog post and had left the last parts, but I'll continue that with that in another blog post reading stream. So let's start. Now this is loading. This is a paper I want to read in this stream. The next one is this other little paper. The next one is we'll read about 5 to 6 papers. So let me set these up, and I'm going to take notes. So in my terminal. See. Stream. Sorry. Yeah. And I just have to, in my settings, I just have to change this real quick. So Bluetooth, or let me just get to keyboard. Was it? I have to change my caps lock key to escape in this session. This normally I have this set in my own setup, but because this is my streaming setup, I don't have this mapping, and it's really hard to use Vim when you have caps lock as caps lock. And why didn't this change? Magic keyboard. Escape. Magic keyboard. Yeah, now it's working. Oh yeah, without losing any more time, let's start with our paper, which specifically introduces the LOHA adapter and the locker adapter. So most of the time I don't read papers in order, so I first read the abstract. Text image generative models have garnered immense attention for their ability to produce high fidelity images from text prompts. Among these, Stable Diffusion distinguishes itself as a leading open source model in this fast growing field. However, the intricacies of fine tuning these models pose multiple challenges, from new methodology integration to systematic evaluation. Addressing these issues, this paper introduces Lycoris, LoRa beyond conventional methods, other rank adaptation implementations for Stable Diffusion, an open source library that offers a wide selection of fine tuning methodologies for Stable Diffusion. Furthermore, we present a thorough framework for systematic assessment of varied fine tuning techniques. This framework employs a diverse suite of metrics and delves into multiple facets of fine tuning, including hyperparameter adjustments and the evaluation with different prompt types across various concept categories. Through this comprehensive approach, our work provides essential insights into the nuanced effects of fine-tuning parameters, bridging the gap between state-of-the-art research and practical application. Now, let me just look at the conclusion part. Concluding remarks. And it seems there isn't. Oh, so let me just have an overall paper. This is a interesting point it makes. It says that the LoHa adapter seems to be better suited for multi-concept and simple instance training, while Locr is better suited for complex single concept tasks. This could be a key takeaway from this paper. The distinction in their applicability also indicates that the rank of the matrix update, often considered a key factor, may not always be the definitive predictor of a method's efficacy in various fine-tuning scenarios. Despite our extensive efforts, the scope of our study remains limited. For example, we have not explored the task of generating images with multiple learned concepts, as this aspect is highly sensitive to input prompts and more challenging to evaluate. However, recent works such as Huang et al. Aim to address these issues. And we believe that incorporating these emerging evaluation frameworks will further enrich the comparison of fine-tuning methods in future studies. Okay, so that's great. Now let's look at the figures. So this was a technique I learned from a blog post, and I don't know, it seems like it helps me internalize the paper much faster than reading it in order. So here there's a matrix product, which is the standard LoRa adapter. Here we have two LoRa adapters, and there is a Hadamard product, which is the entry-wise product. Here there is a LoRa adapter, I believe, and the LoRa adapter has dimension rank R, and there are other dimensions called VP, VQ, UP, UQ. I'm not sure what this paper uses these notations for, but we'll see, I guess. Let's continue. In figure 2, there are a couple of plots, maybe with given confidence intervals, but these are not actually that readable. So I don't like how this paper is written. I've looked at this paper. I skimmed through it before, and these are not very readable. So I guess I can take lessons, some, to not do this in my own paper. So it says image similarity alter, image similarity SCD trigger, image similarity train, SHAP. SHAP B-swarm charts and scatter plots for analyzing the impact of change in different algorithm components. In the B-swarm plots, LoRa is in blue, LoHa is in purple, Local is in purple red, and native fine-tuning is red. Model capacity is adjusted by either increasing dimension for LoRa or LoHa or decreasing factor for Local. In the scatter plots, SCD indicates we use squared centroid distance to measure image similarity. This removes the implicit penalization towards more diverse image sets in the computation of average cosine similarity. We believe thus it is thus more suitable when we are interested in the trade-off between fidelity and diversity. Qualitative comparison of checkpoints trained with different configurations. Samples of the top row are generated using only concept descriptors, while samples of the bottom row are generated with the two prompts. V castle scene stands against a backdrop of snow-capped mountains, and V castle scene surrounded by a lush, vibrant forest. The number of training epochs is chosen according to the concept category. These images are just too small, but there's dimension 16, alpha 8, Loha dimension this resulted in very blurry picture. I can't even zoom much more. This maximum amount of zoom I can do is 500%, and even this is too small, but I believe Locker adapter has resulted in very blurry images. The dimensionality is actually really high, and the alpha convention used is there is no convention, so these two have the same dimension. This has a lower alpha, which corresponds to a lower learning rate, and we see that the diversity is more, and here there's almost no diversity between the generated images. it's almost fully overfit. Let's continue. Here we see a table, a tentative ranking based on different evaluation criteria for the methods we explore in our experiments. Native. So I believe native is for full fine tuning. I'm not really sure, but if that's the case, it's the best in terms of fidelity. In terms of diversity, it's the worst as we expect because there are no constraints on the optimization. For the case of LoRa, it is it has higher fidelity than Locker. It has lower fidelity than Loha. But do these have the same ranks, or do these have the same number of parameters? So it hasn't stated any of this. The controllability is maybe prompt following. The capacity of it to follow prompts, and diversity is self-explanatory, I guess. So that were all the plots. So this paper doesn't really have much plots. So let's mostly skim over the introduction parts, and then we will dive maybe deeper into the method part. But there isn't really a complicated method. I just have to look up the dimensionality and how the Kronecker product is computed. Hadamard product is very straightforward. So here it explains stable diffusion. Model customization with LoRa to enable more personalized experiences. When integrated into the model customization process, lowering adaptation could substantially reduce the number of parameters. Where gamma is a merge ratio that balances the retention of pre-trained model. We further define alpha as gamma times R. So as the rank increases, if alpha is static, gamma decreases. The Lycoris library. So this is the method. LoRa beyond conventional methods. Broadly speaking, the library's main objective is to serve a testbed for users to experiment with a variety of fine-tuning strategies for stable diffusion models. seamlessly integrating into the existing ecosystem. Lighthorse is compatible with easy-to-use command line tools. Okay. For most algorithms implemented in Lighthorse, stored parameters naturally allow for reconstruction of the weight update. Okay. Implemented algorithms. For conciseness, we will primarily focus on three main algorithms: LoRa, LoHa, and Looker. The merge ratio alpha over R is implemented. Setting gamma is mathematically equivalent to scaling the initialization of B and A by square root of gamma and scaling the learning rate by square root of gamma, or gamma, depending on the used optimizer. In the work of Hu et al., the focus was centered on applying ROLRIC adapter to the attention layer within the large language model. In contrast, the convolutional layers play a key role, and this is implemented. So, LoHa, inspired by the basic idea underlying LoRa, we explored the potential enhancements and fine-tuning methods. In particular, it is well recognized that methods based on matrix factorization suffer from the low-rank constraint. Within the LoRa framework, weight updates are confined within the low-rank space, inevitably impacting the performance of the fine-tuned model. To achieve better fine-tuning performance, we conjecture that a relatively large rank might be necessary, particularly when working with larger fine-tuning data sets, or when the data distribution of downstream tasks greatly deviates from the pre-training data. However, this call leads to increased memory usage. FedPara is a technique originally developed for federated learning that aims to mitigate the low-rank constraint when applying low-rank decomposition methods to federated learning. One of the advantages of FedPara is that the maximum rank of the resulting matrix is larger than those derived from conventional low-rank decomposition. So this is a LoRa adapter, this is a LoRa adapter, and there is a Hadamard product between. The rank of delta W can be as large as R squared. To make a fair comparison, we assume that the low rank dimension equation 2 is 2R. So that they have the same number of trainable parameters. The LoHa method is really straightforward. So, in the same spirit of maximizing matrix rank while minimizing parameter count, our library offers Looker as another viable option. This method is an extension of the Crone technique initially proposed by et al. I should add citations to Importantly, we have adapted this technique to work with convolutional layers, similar to what we achieved with Locon. A unique advantage of using Kronecker products lies in the multiplicative nature of their ranks. Going further, to provide finer granularity for model fine-tuning, we additionally incorporate an optional low-rank decomposition, which users can choose to apply or not. that focuses exclusively on the right block resulting from the Kronecker decomposition. So they further propose to decompose this into two parts. So here, I'm not sure what they set alpha and gamma to. Um, they say alpha is. Where do they say that? That's actually a very important part in determining the results. So here it says gamma equals alpha over R, which is the merge ratio. But what do they set alpha and gamma to? We'll see in the experiments part, hopefully. And I want to further delve into this Kronecker product part. So let me just open. Tell me what Kronecker product is in detail. The factor f and dimension r. Vp by Vq, Up by Uq. Vp is P over Up. Up is the maximum. What is this guy saying? Let A be an m by n matrix and B be a p by q matrix. The Kronecker product is an m by m times p, so m times p, and n by q block matrix defined as, in essence, you take each element it is non-commutative, associative, distributive, respects the transposed. Okay. So I get the definition of the operation. And given this, let's see. Looking at the diagram again, we have C Kronecker product with B times A. And we want U times VP to be our pre-trained matrix row dimension. So it's P by Q. UP times VP must be equal to P. And UQ times VQ must be equal to Q. UQ times VQ must be equal to Q, but nobody wrote such a thing. So we assess the similarity between the generated and dataset images using average cosine similarity and squared centroid distance between their Dino V2 embeddings. The alignment between generated images and corresponding prompts is measured by a clip. Diversity of images generated with a single prompt is measured by the Venn score. What is a Venn score? We had a stream on evaluating generated images, and we didn't discuss this at all. Venn uses a proprietary scoring system to evaluate the condition and value of... No. It is formally defined as the exponential of the Shannon entropy. Von Neumann entropy are the eigenvalues derived from a similarity matrix K. This similarity matrix is created by applying user-defined pairwise similarity function K to all pairs of samples in the set. So the alpha of LoRa, the dimension of LoRa is 8, alpha is 4. Dimension of LoRa is 4. Dimension and alpha. So alpha is equal to 2. And R equals 4. Thus gamma is equal to 2. Am I right? Or is it equal to? Oh, sorry, it's written above. 1/2. How is this implemented in the check how this is implemented in the pet library? This factor is set to 8 and the other part is not decomposed. We might need to decompose to achieve lower parameter counts. So let's continue. Model customization, model evaluation. We're in the 36-minute mark. In this section, we demonstrate an equivalence between the scaling, the merge ratio, and scaling the initialization parameters and the learning rates. Why theorem 1 provides an intuitive. These were introduced to solve numerical issues. Tucker decomposition. This is what they used for convolution layers, but this is not of interest to me at the moment, and it is not the industry standard to tune convolution layers, so I think we can just skim over this part. There's an image similarity section. The unreliability of metrics. So I think this is all we can get from the first paper. Overall, it's a comprehensive paper, and they've really pointed out some issues with metrics. They've delved deep into some metrics. They performed extensive evaluation, but the paper could be written better in terms of overall how everything is presented. Now let's move on to the other little paper, adaptive LoRa. But before that, I want to check the path GitHub. So here, when I go into tuners and something like Aloha and look into the configuration. So this is the alpha parameter. But when applying this, does it actually divide the output by R before scaling it? So I want to check this out. So alpha self.scaling alpha over R. Wow. They actually do. But why just they scale by the number of parameters? Then would it be smart then let me look at the FuriFT adapter and then look at there and find the scale or scaling. It just multiplies it. It doesn't take into account any number of parameters. So this is a problem. This is actually not a problem, but it's good that I realized this. Now let's move on to the other little paper. Adaptive budget allocation for parameter efficient fine-tuning. So this paper addresses a problem with the LoRa adapter, which is it allocates parameters with respect to how proportional to how big the matrix is. So let's say I have an m by n matrix, and let's say I select the rank to be 4, then this matrix gets allocated m plus. So there are two matrices, m times 4, and there's another matrix which is 4 times n, which makes the total number of parameters, as 4 times m plus n. So, but it is not actually smart to do this because some layers are not really that important in determining what the output is going to be. So this paper tries to address this issue. So fine-tuning large pre-trained language models on downstream tasks has become an important paradigm in NLP. However, common practice fine-tunes all of the parameters in a pre-trained model, which becomes prohibitive when a large number of downstream tasks are present. Therefore, many fine-tuning methods are proposed to learn incremental updates of pre-trained weights in a parameter-efficient way. For example, low-rank increments. These methods often evenly distribute the budget of incremental updates across all pre-trained weight matrices and overlook the varying importance of different weight parameters. As a consequence, the fine-tuning performance is suboptimal. To bridge this gap, we propose ADALR, which adaptively allocates the parameter budget among weight matrices according to their importance score. In particular, ADALR parameterizes the incremental updates in the form of singular value decomposition. Such a novel approach allows us to effectively prune the singular values of unimportant updates, which is essentially to reduce their parameter budget, but circumvent intensive exact SVD computations. We conduct extensive experiments with several pre-trained models on natural language processing, question answering, and natural language generation to validate the effectiveness of ADALR. Results demonstrate that ADALR manifests notable improvement over baselines, especially in low budget settings. Our code is publicly available at this button. Now, let's look at the conclusion. We propose a parameter efficient fine tuning method, ADALR, that adaptively allocates the parameter budget according to importance scoring. In ADALR, we parameterize the incremental updates of weight matrices in the form of singular value decomposition. Then we dynamically allocate the parameter budget among incremental matrices by manipulating the singular values based on a new importance metric. This approach effectively improves the model performance and parameter efficiency. We conduct extensive experiments on natural language processing, question answering, and natural language generation tasks. Results show that ADALR outperforms existing approaches. Now let's look at the figures. Given the total trainable parameters as 280 to 80,000, we apply LoRa only to selected weight matrices. Or selected is on the right, the Barta V3 base, and they compare the fine-tuning performance on MNLIM. Figure they do an ablation on which layers to fine-tune, which is understandable. Here we have the first algorithms. Dataset D, total iterations, T, budget schedule, B, hyperparameters, eta, gamma, beta 1, beta 2. Sample mini batch from D and compute the gradient. Compute the sensitivity IT in 8 for every parameter in P epsilon Q. Update I bar T as U bar T 10. Then compute SKIT for K equals 1 to R. Update gradient. Perform gradient update. Then update the singular values. Here there are results. We see that they perform really well, but I want to know the confidence intervals. We report mean of 5 runs using different random seeds. I wish they put confidence intervals, because I'm not sure if these results are statistically significant. results. Oh, I need a piece of paper. Okay, I had something in my mind I had to write down, so I didn't forget. Now let's look at the paper. So, introduction, a standard introduction. In the introduction, they introduced the LoRa parameterization. They introduced their own method. In the introduction, they say that they parameterize the adapter to mimic an SVD. P and Q represent the right and left singular vectors. Because these are not actually singular values, they have to use importance scoring. Because if this was a normal SVD decomposition, we know that the most important part in reconstructing the full matrix would be the first singular value. But this is just a parameterization that seems like an SVD, which is not actually a singular value decomposition. So they describe the importance metric and a budget scheduler. A typical transformer model consists of L-stacked blocks, where each block contains two submodules. Low rank adaptation. They go into this once more. So, now we have come to the methodology part. As mentioned in section 1, we propose to parameterize the incremental updates of the pre-trained weight matrices in the form of singular value decomposition. We have big, is that a big lambda? Let me just check. Yes, it's a big lambda. The lambda is initialized with 0, while P and Q adopt a random Gaussian initialization to ensure the difference is 0 at the beginning of training. To enforce the orthogonality of P and Q, they implement a regularizer. In our method, lambda is iteratively pruned. Okay. Importance of wear rank allocation. This paper is really well structured and written, and really seems nice to read. We apply the SVD based adaptation to every weight matrix. In order to control the budget, we iteratively prune singular values in correspondence to their importance score during training. For clear reference, we use K to index the incremental matrix. So K is the kth layer. And for E in the kth layer, I is the ith singular value, pseudo singular value, and it has an importance score. The given importance score. It didn't say how it computes the importance score. Then given importance score ST, the singular values are pruned following top B. So sensitivity based. So it measures importance based on sensitivity. We are in the 57th minute. We calculate the mean importance of P and Q such that SKI. So S lambda Ki, so the importance of our singular value is how did it define sensitivity? It didn't define it yet. It will later define it, but let's say it's the sensitivity of P and Q average. Here S is the specific importance function for single entries. We can adopt the sensitivity for S, which is defined as the magnitude of the gradient weight product. So every weight times its gradient, where Wij is any trainable parameter. 8 essentially approximates the change in loss when a parameter is zeroed out. If the removal of a parameter has large influence, then the model is sensitive to it, and we should retain it. However, point out that sensitivity in 8 is not yet a reliable importance indicator. Such a score is estimated on the sampled mini-batch. The stochastic sampling and complicated training dynamics incur high variability and large uncertainty. Therefore, propose to resolve this issue by sensitivity smoothing and uncertainty quantification. So here, we measure the importance of an entry by having a beta and a there is a momentum introduced. That's great. So there's a momentum introduced, so we further complicate things and we introduce a momentum to the prior sensitivity, which essentially smooths out this process because each mini batch could affect things differently. Let me think. Like if you're for like the personalization task, if your batch size is equal to your instance data set size, I believe that you shouldn't need a complicated sensitivity function like this. So you could just simply use the previous one defined in 8. And why does it have absolute value here? UT is the uncertainty term quantified by the local variation between. Oh, then we estimate uncertainty from the smoothed out difference between the smoothed out and the current version. Oh my god. How much more complicated could this become? And we have a global budget scheduler. So this tries to schedule how the singular values are going to be pruned to achieve our target rank. We call that we set the initial rank, we warm up, then follow a cubic schedule to decrease the budget. Then the experimental details are performed. So they do their tests on V100 GPUs. I don't really want to dive in really deep, but I just want to look at what they set. They I really they don't have an alpha parameter here. They just set the learning rate to 10 to the minus 3. Depending, they change the learning rate depending on tasks. Hopefully they also use the optimal learning rate for comparison, but I'm not really convinced that they did, and search for parameters. But nevertheless, let me just check. Fix alpha as LoRa. interesting thing is that they didn't put any ablations on why they. What if they didn't use momentum, and what if they didn't use uncertainty estimation? So I wonder how effective these extra steps defined here are. And let's move on to our next paper. We have completed about the first hour, but and then let me think. I have read about 3, and then now we have Vera. Maybe I'll look at Fourier FT. Was there any other thing I wanted to look at? Let me check my notes for a second. I don't think so. Maybe we could. I'm not sure if it's necessary. I want to look at. So, not you. You. Parameter. Efficient fine tuning using the discrete Fourier transform. I have this open. I should have used a bigger font size for the stream, but whatever. Now we have Vera, we have Fourier FT, and $13,000 citations. So lowering adaptation. LoRa is a popular method that reduces the number of trainable parameters when fine-tuning large language models, but still faces acute storage challenges when scaling to even larger models or deploying numerous per user or per task adaptive models. In this work, we present vector-based random matrix adaptation Vera, which significantly reduces the number of trainable parameters compared to LoRa, yet maintains the same performance. It achieves this by using a single pair of low-rank matrices shared across all layers and learning small scaling vectors instead. We demonstrate its effectiveness on the GLUE and E2E benchmarks, image classification tasks, and show its application in instruction tuning of 7B and 13B language models. Now let's look at the conclusion. This is an ICLR 2024 paper. In this work, we introduce a fine-tuning method that significantly reduces the number of trainable parameters compared to LoRa, yielding similar or better results on downstream tasks. Specifically, it achieved 10-fold reduction in parameters, yielding the same performance on the GLUE benchmark for Roberto Large, 10-fold reduction on image classification tasks, and 3-fold reduction on the E2E benchmark. While the current study focuses on language and vision models with transformer architecture, so yeah. It claims to achieve a tenfold reduction in image classification, glue benchmark, and E2E benchmark. But the major problem with these tasks are these are really high level tasks, and you can really overfit models to these tasks. But when it comes to my experience with generative models or other kinds of tasks, low level tasks, it's really hard for a model to fit to these tasks. So you can't really achieve this much reduction. So maybe I can add this to my notes. So with high level tasks, you can achieve much more efficiency compared to low level tasks with parameter efficient fine tuning. Now let's look at the figures. We have lower on the left, we have Ver on the right. We have two frozen low rank matrices. We train a scale and a bias. Ah, is that just a number or a vector? So that's a vector. That's a vector. That's strange. We will check the dimensionality later, but I'm not sure. Required bytes. They reported the required bytes. They compared to different methods. More tables. It's really important for how long you also train these models. So if you just train them for less steps, then you could get a closer benchmark to the compared methods if they have more capacity. But if you continue on training, because the bottleneck for your model would be the capacity of the model, and they would have a higher capacity, they could surpass you easier. So I want to actually know for how long did they train the model, and was it saturated? They report confidence intervals if they are unique. Let's return to the start. Now, introduction. I got my glasses. In the area of increasingly large energy, they introduced different methods. Frankel and Carbon identified that randomly initialized neural networks contain subnetworks that are capable of reaching high performance when trained. Ramanujan et al. Revealed that there exist subnetworks that can achieve impressive results even in the absence of training. I want to add these to my notes. Maybe they'll be useful. Why then am I not using a proper clipboard setting? No, I am using it. So let's read the method part. In this section, we introduced vector-based random matrix adaptation, a novel parameter-efficient fine-tuning method that builds upon and extends the state-of-the-art method LoRa. A has shape M by R. And these are diagonal matrices. These are not vectors. Did they denote this? They said vectors here. But here they say at least write a Hadamard product or something there, so it's more understandable, but I get it now. So, but the dimensionality is also incorrect. B has to have shape N by R. B has to have shape M by R, and A has to have the shape R by N, so they cancel out. When you read papers in detail, you see how many mistakes they make, and it's pretty funny. So let's say that a model has 560 layers. And in these 560 layers, our average layer matrix size is 1250. Setting R equals to 256. We learn two diagonal matrices which would have 1500 layers, parameters per layer. long ago? So we're almost at 1.5 hours. So instruction tuning, but I got the main gist of it, at least. I'm going to look at I didn't look at the language model benchmarks. I'm just curious. First of all, did this paper use a scale? Let's see. Did they? Let me just copy this just for. They don't use an alpha. So okay. They shared their hyperparameters. And I believe that it takes more time than there are the results. So these two could be our last two papers. Maybe I can do a separate thing for the LoRa paper, depending how I feel after I finish the Fourier transform paper. But let's see. LoRa adaptation has recently gained much interest in fine-tuning foundation models. It effectively reduces the number of trainable parameters by incorporating LoRa matrices A and B. Despite LoRa's progress, it faces storage challenges when handling extensive customization adaptations or larger base models. Here we introduce Fourier FT, which applies inverse discrete Fourier transform. Empirically, our Fourier FT method shows comparable or better performance with fewer parameters than LoRa on various tasks. The code is released. Now let's read the conclusion. In this paper, we aim to achieve an extremely low storage memory for a single fine-tuning of large foundational models. This will enable the customization of multiple fine-tunings for different domains, tasks, or user preferences. To achieve this, we propose a simple yet powerful fine-tuning method that treats weight changes as spatial domain matrices. Only learns the sparse coefficients in the spectral domain. Compared to LoRa style baselines, our approach reduces the number of trainable parameters by about 8 times 500 on a wide range of tasks in the NLP and computer vision domains. Now let's look at figures. So figure 1. Number of parameters are on the x-axis, while accuracy and score assigned by GPT-4 on instruction tuning. And they actually tested for just 2 configurations. which I would think be insufficient, but who knows. The left side shows instruction tuning. The black circles represent full fine tuning. Figure 2. Random entries are selected per model, which are then used throughout the model, and the coefficients are trained. These random coefficients. So the weight change is represented by their multiplication. Okay. They perform inverse discrete wavelet transform. We have algorithm 1, which shows this. So pseudocode. Self.d1, self.d2, self.n, self.alpha. This alpha is not the same as the other alpha. This should be actually gamma, but because they use the same thing, it's pretty hard if you don't read in detail. They can't do a per rank adjustment. Entry initialization, no frequency bias. They initialize entries and they initialize spectral coefficients with Gaussian initialization. Then they take the inverse Fourier transform, multiply it by alpha, and they add the output of the base there with the matrix multiplication between x and delta w. There are different tables reporting different values. And then in the appendix, also in this paper, there are no confidence intervals, which we can determine if the findings are statistically significant. There's a small little experiment which reports only the FID, which is like FID is not a very stable matrix, also metric. Also, you like in the Dreamboot task, you want to see if the identity is preserved, etc. You don't want to, the only goal isn't to optimize for realism. They just provide a couple of examples. This is a fun little experiment they performed. They want to perform classification on this, and they design a classification task. They train a single layer and look at how effectively it can fit. But actually, I don't think this is an apt experiment, because let's say you want to match an input vector to an output vector, and uh, for any given input and output pair, if there's only one, then you could find a linear mapping which is has low parameters. So let's say the hidden layer would have uh, we don't even need to have it. Let's just say we have a matrix multiplication, a diagonal matrix with 0 entries in the other parts and trainable parameters in the diagonal. We could just fit it directly. We could just scale each entry to our liking and just get the output. So in these tasks where it's easy to overfit, having more rank provides an incredible advantage. But when the task becomes more complex, things don't really, you have to approximate nonlinear functions, and things aren't that clear that if you have higher rank, we would attain better results. So this is not actually I think the advantage of taking a Fourier transform. This is just an advantage of having a higher rank matrix, which you could obtain by just having a blank matrix and randomly initializing values. So I looked at the appendix. So let's now continue to the introduction part. I'll just skim over the introduction. I'll look at the methodology a bit more in detail, and then maybe we could start wrapping up. So we're at the 1.5 hours mark. Large foundation models, LFMs have demonstrated exceptional performance. Blah, blah, blah. Now they formulate LoRa. So image matrices and one-dimensional signal vectors are different because they're the data matrices, but these are the model parameters. So you know that image matrices are locally smooth and etc. So they, when you get the Fourier decomposition and you take the low frequency components, you can mostly construct the image, the semantics of the image at least. You would get a blurry image, but you know this, but with the parameters of model, there's nothing enforcing local smoothness. So we aim to aggressively reduce the number of trainable parameters for fine-tuning LFMs. To this end, they propose Fourier FD. They have a related works part here. Parameter efficient fine-tuning, non-weight based methods. So we're not really interested, but this is an interesting topic. But these don't seem like very effective methods to my knowledge. So we didn't read any prefix tuning or other papers on this. We're interested in weight-based methods. So sparse Fourier transform in deep learning. There is a small introduction to this, and now we come to the method part. So we present Fourier FD, a parameter efficient fine-tuning method. So the forward pass, here there's the lower decomposition. Here we have our forward pass. So first of all, we initialize random coefficients in our residual weight matrix. We initialize them with Gaussians, and we take the inverse discrete Fourier transform. And after we take the inverse discrete Fourier transform, and take the real part, we multiply it by our input vector and add it to our normal output vector, and we use the scale alpha here. So the proposed forward pass is this, and they perform an ablation on the initialization of the coefficient matrix. So they initialize the coefficient matrix with certain biases, and they find that the best bias is no bias at all. So they uniformly sample the entries to which they set trainable. My intuition would be also this, because if like there were local smoothness constraints on the parameter matrix, maybe biasing it towards the lower frequency components would yield better results, but because there are no constraints on the parameter matrix, that makes sense. And now we have our experiment section. Other methods, some of them we have covered, are mentioned here, and here are the implementation details. I'm not really interested in the language model implementation details. So, and instruction tuning, I guess here they provide again image classification results, which some of the other papers provided, which are easy to overfit once again. Here they perform an ablation. Rather than the inverse Fourier transform, they use a random basis or an orthogonal basis and look at the results. These results don't seem that convincing because, first of all, there are no confidence intervals reported. Second of all, actually, they tuned the hyperparameters of the model according to the Fourier basis, which you can see there. They just selected the hyperparameters in a really detailed manner. But for the other basis types, they didn't really search hyperparameters. So these are the optimal learning rates and the optimal number of training steps, epochs, scales for the case of the Fourier basis. So that could make a huge difference, which in this case is like the orthogonal basis 4% lower, but this just could be the effect of just tuning the hyperparameters. So maybe actually because the Fourier transform is inverse discrete Fourier transform is linear and they are orthogonal, this could be just an arbitrary selection of basis vectors which doesn't give any context or any extra advantage. So we are about 1 hour and 40 minutes in. We have the original Laura paper. I want to do a deeper dive. I'm a bit tired right now because I spoke too much, but yeah, we could proceed with other PEFT methods, parameter efficient fine tuning methods, in later streams. So just let me, yeah, everything seems to be looking fine. Thanks to everyone for listening. See you in the next parameter efficient fine tuning stream, or before that, maybe I'll do other streams, but yeah, see you then. Bye.